Hello, and welcome to another Digital Differential Equations lecture video for Salt Lake Community College. In this video, we are going to be going through Chapter 3.4, Determinants and Cramer's Rule. In Chapter 3.4, we introduce the determinant of a square matrix and use it to determine invertibility of a square matrix. We will then look at Cramer's rule, which is another useful application of the determinant. Cramer's rule can be used to find the solution of a system of equations ax equals b when the coefficient matrix A is square. Let's start with some definitions. The determinant of a square matrix A is a scalar, which is a single number that is associated with the matrix. There are several useful applications of the determinant. However, in our class, we will just be using the determinant to solve systems of linear equations. Now, one of the things you probably have noticed that I've emphasized so far is that our matrix that we're working on must always be square. You can only take the determinant of an n by n matrix. It must have the same number of rows and columns. Properties of the determinant. The determinant of the identity matrix is always equal to 1. If you ever have a row of zeros in your matrix, then the determinant is going to equal 0. If one row is ever a multiple of another row, then again the determinant is going to be 0. If one column is ever a multiple of another column, again the determinant will be 0. And then now the most useful applications of the determinant for us today will be that if the determinant, let me change the color and highlight this one. If the determinant of A is equal to 0, then a matrix is singular. And what you want to know by this is that your matrix does not have an inverse. A inverse does not exist. However, if the determinant of your matrix is not 0, then your matrix is non-singular, meaning A inverse does exist. These terms are ones that you will see come up in future sections, so try and get a handle on singular and non-singular now. There are several methods that we have for calculating the determinant of a matrix that would depend on the size of the matrix. Of course, the simplest determinant that we'll talk about is when you're talking about a 2 by 2 matrix. So for a 2 by 2 matrix, your determinant, and notice the notation, it has the vertical bars on each side. Your determinant is always going to be the product of AD minus this off diagonal CB. Notice that this is one of the parts of the formula we used back in chapter 3.3 for finding the inverse of a matrix. Specifically, you probably recall that A inverse is defined to be 1 over AD minus BC times another matrix where you switch the main diagonal entries and negate the off diagonal entries. With this new representation for the determinant, we probably could actually now write this as 1 over the determinant of A times the matrix associated with A. So determinants. Notice this is also a reason why you notice that the determinant cannot be 0. Because if the determinant is 0, then you're dividing by 0 right here. So the determinant must not be equal to 0 for A to be non-singular, for the inverse to exist. If you're given a larger matrix, a 3 by 3 matrix, then we can still find the determinant. We cannot use the same shortcut, but we do use what is sometimes referred to as the basket weave method. To find the determinant of a 3 by 3 using the basket weave method, you will copy down the first and second columns and rewrite them at the end of your matrix. So take these two columns, copy them down, and append them to the end of the matrix. Now to find the determinant using the basket weave method. You look at the products of the diagonals going to the right. So you look at the product of AEI plus the product of BFG plus the product CDH minus the sum of the products going in the other diagonal direction, GEC plus HFA plus IDB. Notice how it creates the woven basket image by how you're doing your products. So, determinant of a 3 by 3 matrix. For any larger matrix, so let's just call it n by n, for our example here, I've shown you a 4 by 4 matrix, but this method would apply to larger matrices as well. So for any larger matrix, we use the expansion by cofactor method. The expansion by cofactor method uses the signs matrix. To help us keep track of signs that go in front of each of our coefficients. And to give you an example how the expansion by cofactor method works, we will do a little layout for this 4 by 4. And your starting point is to always pick a row or a column to expand upon in your original matrix A. It does not matter which row or column you expand on. Your answer will be the same in the end. For this example, I'm going to choose to expand along row 2. And then we'll use the signs matrix to figure out the coefficients of each of our factors. So here's what I mean. We'll first expand on this row A2, or the second row. And when you expand on this row, the first item you look at is this coefficient A21. And you expand on that column containing A21. Or maybe cancel that column is what I mean, A21. So in your matrix down below, your product, what you should see is your coefficient A21. And notice it's negative. It's because A21 is in this negative position here. Now, when you're expanding on this row and you're canceling this column, you'll notice it leaves 6 entries that are not canceled out. There's the A12, A13, A14, A32, A33, A34, A42, A43, A44. And notice that those are the entries that appear in this matrix here. It's a smaller determinant than the original, and it has the A21 as a factor, as a coefficient. Okay. Then you expand, or you cancel the next column. So the next column contains the A22 element. This one. When you're at the A22 element, that now becomes your coefficient. Notice the sign is now positive because the A22 is in the 2-2 position. And when you're at the A22 element, you cancel that column, and you should notice it leaves 6 entries in your matrix that are not canceled out. It would be the A11 entry, A13, A14, A31, A33, A34, A41, A43, and A44, which you'll see are the entries in this smaller 3x3 determinant. Okay. When you get to the next entry in this row that you're expanding on, you're going to be at the A23 entry. And you're going to cancel this column that it's in. And when you cancel that column, again, you should notice it leaves 9 entries that are not canceled out. Now the A23 will be our coefficient. Notice the coefficient of A23 is now negative. And if you look at the entries that are not crossed out, you have your A11, A13, A14, A31, A32, A34, A41, A42, and A44, which show up in this smaller 3x3 determinant. Okay, looks like there's one more to go. So now we get to the last entry in this row that we're expanding on, which is the A24 entry. Notice that the A24 entry should end up being positive. And when you're at the A24 entry, you'll cancel the column that A24 is in, which again should leave 9 values that are not canceled. The A11, A12, A13, A31, A32, A33, A41, A42, and A43, which show up in the entries of this smaller 3x3 determinant. What you should notice by this example, or by looking at this form, is that we can evaluate an n by n determinant by rewriting it as a linear combination of smaller determinants. But it's still somewhat of an involved process. How about we look at some examples to see how we'll calculate the determinant? Let's look at some first ones, some 2x2 matrices. What I would like you to do in this example is to find the determinant of each of these 2x2 matrices and then use the determinant to determine if the matrix is the invertible. Now remember, for 2 by 2 matrices, the way we calculate our determinant is by looking at the product of the main diagonal minus the product of the off diagonal. So here you'd have 2 times 3 minus 1 times 5. So notice that this is 6 minus 5, which is equal to 1. For this matrix, we want to know that A inverse exists. Oftentimes when calculating our determinant, many of these calculations we do in our head. For example, when I do this one, negative 3 times 4, the product of the main diagonal, negative 12, minus the product of the off diagonal, which is 0 times negative 1, 0. This determinant is negative 12. Now, negative does mean something in other applications of the determinant. However, for us, we want to know that this is not 0. And because the determinant is not 0, we can say with confidence that A inverse exists. I'd like you to go through and calculate the rest of these 4 determinants for me. If you could, please pause the video as you calculate them, and afterwards we'll come back and we'll talk about what you should have observed. I'll see you in a moment. Okay, I hope you paused the video and calculated these determinants. Let's have a look at what you should have seen. Now with this matrix, our determinant will be the product of this main diagonal, which is 10, minus the product of the off diagonal, which is also 10. Notice that this is now equal to 0, and so this tells us A inverse does not exist. Now, one of the things we should have observed, though, when looking at this matrix, is that in this matrix, technically your second row is 2 times the first row. And because one of your rows is a multiple of another, we probably could have just identified right away that our determinant had to be 0. Let's got another one. Here, the determinant, the product of the main diagonal, is going to be 4 times 0, which is 0, minus the product of the off diagonal. 1 times 0 is also 0, so that this determinant is 0, and we can conclude that A inverse does not exist. Again, if I were to look at shortcuts in the future, I would have want to identify that there is a row of zeros in our matrix. The determinant will have to be 0. Okay. Another one here. The determinant of this matrix, look at the product of the main diagonal, which is 15, minus the product of the off diagonal, which is also 15. So again, here the determinant is 0. A inverse does not exist. And our last one, identify that this is the identity matrix. When given the identity matrix, we still find our determinant the same way. The product of the main diagonal, 1, minus the product of the off diagonal, 0. And so here, your determinant is equal to 1 again. But as a shortcut in the future, we can identify that anytime we give you the identity matrix, the determinant is always going to be equal to 1. So determinants of 2 by 2 matrix, pretty friendly. Let's look at the determinant of a 3 by 3 matrix. So here I want you to find the determinant of each 3 by 3 matrix using the basket weave method. Then use the determinant to determine if the matrix is invertible. So if the A inverse exists. So for the basket weave method, I'd like you to recall that you always copy down your first 2 columns. Oh, that's a terrible looking 3. And now for the basket weave method, you look at the products of these main diagonals going down to the right. So look at the product of 3, 0, 4, 4, 2, 0, 1, 1, 2. So here the determinant would be the 3 times 0 times 4, because that's 0, it's going to be 0, plus 4 times 2 times 0 is going to be, again, 0. 1 times 2, plus 2. Minus the products of these off diagonals that go up and to the right. So look at the product of 0 times 1, 2 times 2 times 3, 4 times 1 times 4. Notice that it got kind of tricky right here because I didn't write my 3 over very much. Make sure you write these in nice columns when you do it. So 0 times 3 is going to be 0. 2 times 3 is going to be 12. Four times 1 times 4 is going to be 16. If I simplify this, I think we get 2 minus, see, 12 plus 16 is 28. Which is equal to negative 26. We can say for certain that A inverse will exist, or put it another way, say that A is non-singular. I'd like to give you a moment to calculate the determinant of our next 3 by 3 matrix. So if you could, pause the video for a moment, test yourself, and see how you do. I'll see you back here in just a moment. Okay, let's see how you did. So again, when we're using the basket weave method, we want to copy down the first 2 columns of our matrix. And now we look at the products of the diagonals. So first we look at the product of these diagonals moving down and to the right. So 1, 1, 5, 2, 5, 4, 0, 2, 5. So let me write that out. So 1 times 5 is going to be 5. Plus 2 times 5 times 4. 2 times 5 is 10. 10 times 4 is 40. 0 times 2 times 5 has to be 0. Minus the product of those off diagonals that move up and to the right. So here we're looking at the product of 4, 1, 0. 5, 5, 1, 5, 2, 2. So our first one, 4 times 1 times 0 is going to be 0. 5 times 5 times 1 is going to be 25. 5 times 2 times 2. 5 times 2 is 10, times another 2 is 20. If I simplify what's in the parentheses, I think we get 45 minus 45. Of course, this is 0, which tells us A inverse does not exist. Or we could also say then A is a singular matrix. Hope this makes sense for you so far. Okay, let's move on to n by n matrices. So let's find the determinant of each of these n by n matrices using the cofactor expansion technique, and then use the determinant to determine if the matrix is invertible. So with the cofactor expansion technique, remember you want to choose a row or column to expand upon. For this example, I'm going to choose to expand on the second row. However, remember, it does not matter which row or column you expand upon. You also want to remember your signs matrix. So remember, for the signs matrix, it went like this. Plus in the upper left, and then it alternated minus, plus. If it started with a plus, then it was a minus, and then went plus, minus, plus, minus, plus. So this signs matrix is going to keep track of the signs of each of your coefficients. Now, when you find your determinant, you're expanding on this middle row. You grab your first coefficient, which is a 1. This 1 is going to be the coefficient of another determinant. Here, the sign of this coefficient, according to the signs matrix, is going to have to be negative. So this negative is because of the signs matrix. Now, when you're expanding on this row and you're on this entry 1, you also then cancel the column that this is in. And when you cancel that column, it leaves 4 entries in your matrix that are not canceled out. The 4, 1, 2, and 4. Okay. We then move on to the next entry in our row that we're expanding on, which is this 0. So let me clean up my matrix and get rid of the other row, or the other column that we canceled. So it should look like this. Now, when we're on this second entry, recognize that the second entry, the 0, is in this positive position. So the sign of our coefficient, although it's 0, it's going to be technically positive and then 0. Times a smaller 2 by 2 determinant. Now, although it is going to be 0 because the product of anything with 0 is 0, I want to fill in this matrix for practice. So we'll cancel the column that entry is on. It'll leave 4 numbers not canceled out. The 3, the 1, the 0, and the 4. Okay. Then we go on to our next entry in that row. Let me clean up my matrix some here. So now we're on the 2. And so we'll cancel the column that the 2 is in. Notice again it leaves 4 entries that are not canceled out. Also notice that the coefficient of the 2 would have to be negative. So it would be minus 2 times the determinant of that smaller 2 by 2 matrix created by the digits or the entries that are not canceled out. 3, 4, 0, and 2. So our 3 by 3 determinant has now been written as a linear combination of these smaller 2 by 2 determinants. Now these smaller 2 by 2 determinants we've had more practice with, and so we can take the determinant of those pretty quickly. So here, the smaller 2 by 2 is going to be 4 times 4, which is 16, minus 2, which I think is 14, plus 0 times something, and well, I'm just going to cross that one off now that we know that's 0. So then minus 2 times the determinant of this last 2 by 2 matrix, which is going to be 6 minus 4, which is, oh, not 4, that's 0. 6 minus 0, which is 6. So I get negative 14 minus 12. Negative 14 minus 12. Make sure I got that right. I think it'd be negative 26. Again, what's important to notice about this is that A is non-singular, or that A inverse exists. Okay. I'd like to give you a minute to try our next 3 by 3 example on your own. So if you could, pause the video for a moment and find the determinant of this matrix. I'll see you in a moment. Okay, I hope you paused your video and looked at this next one. Let's see how you did. Now, I probably should have asked you to expand on a particular row or column for practice. I didn't, but I noticed that when I'm looking at this matrix, while I can expand on any row or any column, I'm going to choose to expand on this bottom row. And my thinking is there's lots of zeros in this row. And the presence of those zeros makes a lot of my smaller cofactors 0. Let me show you what I mean. When I expand on this row, the first column we look at is the column containing this 0. And so we cancel this column, which leaves this smaller 2 by 2 matrix that's not canceled out yet. Now, the coefficient is going to be this 0 here. And if we're using our signs matrix, this 0 is going to be positive. So while technically it is 0, I'm going to keep track of my signs for practice. So it's 0 times a smaller 2 by 2 matrix that's not canceled out by these rows or columns. So negative 1, 1, 3, 2. Okay, then we go to the next entry in this row that we're expanding on. The next entry is the 0 entry, this one. So 0. Technically, by our signs matrix, this 0 would be negative. and we'll multiply by a smaller 2 by 2 matrix that's created from when we cancel the column containing that 0. Again, this should leave 4 entries that are not canceled out. It'd be the 2, 1 here and the 1, 2 here. Okay. Then we go to the next entry on that row that we're expanding on, which contains this 4. And if we cancel the column containing that 4, then again it creates 4 entries that are not canceled out. It'll have that 4 as a coefficient. Technically, that 4 by the signs matrix is going to be positive. And the smaller matrix that we multiply by will have the values 2, -1, 1, 3. Now, for simplicity, if I wanted to show less work, I probably didn't have to write these first 2 products because I knew that when their coefficients is 0, the whole thing is 0. But I wanted to practice the technique with you. The only portion that really mattered was this last term. And so here the determinant would be 4 times. If I look at this main diagonal, it's going to be 6 minus the off diagonal, and be careful of your signs, it's 6 minus -1. Which ends up being, this would be +7 here, I think. So 4 times 7 is 28. So that matrix A is non-singular. Or we could say A inverse exists. Okay, we have one left. This is kind of a large matrix, and I don't like taking determinants of large matrices by hand. So I'd like to maybe just first practice what the expansion by cofactors technique might look like for this matrix, but then I'm going to stop and I'm going to show you how to use the TI calculator. So again, with these matrices, we want to choose a row or column to expand upon. And as our last example illustrated, picking a row or column with lots of zeros in them can be helpful. So with that in mind, I'm going to choose to expand on this 3rd row to take advantages of those 2 zeros that are in there. Now, when you expand on that 3rd row, our first coefficient is going to be the 3. And then we'll multiply that by some smaller matrix. That'll not be a 4 by 4, but this will end up being a 3 by 3 matrix. Now let's think about the sign of that matrix, of that 3, excuse me. So remember your signs matrix. It has that pattern to it. Plus, minus, plus. If I added another column, it'd be minus, then minus, plus, minus, plus. Plus, minus, plus, minus, minus, plus, minus, plus. So technically that 3 would be a positive coefficient. Now when you're in that on that 3, you're going to cancel the column that the 3 is in. And it should leave 9 numbers that are not canceled out. So -4, 2, -2. I'm going in rows. So something like that. When we get to the next cofactor, which is this 0, I want to notice it's going to be 0 times some stuff. I really don't care what stuff this is because the cofactor is 0, means everything's going to be 0. And technically, this cofactor is going to be negative. But yeah, I'm not going to write it because I know it's going to be 0. Okay. Then we get to the next entry, the next cofactor, which is going to be that 8. When we reach the 8, we cancel the column that the 8 is in. It should leave 9 numbers that are not canceled out. The 8 is going to be our coefficient. By our signs matrix, we know that the coefficient is going to be positive. We'll multiply that by a smaller 3 by 3 matrix using the entries that are not canceled out. Okay, there's one left. One more cofactor left. So when we're moving on that row that we're expanding on, then now we get to this 0. So the 0 is now going to be our coefficient. It's going to be 0 times a smaller 3 by 3 matrix containing some stuff. I'm not writing it because I know the coefficient is 0, so the whole thing is going to be 0. And technically the sign of this cofactor would be minus. Okay, so this is what the expansion by cofactor technique would look like for this 4 by 4. We would now have to continue and find the determinant of each of these smaller 3 by 3 matrices using whatever technique we wanted. We could use the expansion by cofactors technique again, or we could use the basket weave method. However, I would like to stop with this example because I feel like I'm just doing some arithmetic right now and I'm losing sight of what we want to be focused on. So now what I would like to focus on is how to do this on the calculator. So this would be good practice. So grab your calculator, please. And what I would like to do is find the determinant, and I'm just going to start with this original matrix. So I'll acknowledge that when we're working with these matrices, we never find the determinant of anything large by hand. We will always resort to technology. So your TI calculator is a great tool. And so what I would like to do is enter this matrix into your calculator. So remember the way you do this now, hit the matrix key is located under the x to the -1 button. So hit your second matrix. We're going to need to edit a matrix. Let's choose this first one, A. So arrow over to edit, matrix A. Currently it's a 3 by 3, but we need it to be a 4 by 4 matrix. And now let's enter in our values. Oh, made a mistake. That's probably 8, then 0. When you're entering in signed numbers, negative numbers, make sure you use the negative button, not the minus button on your calculator. Okay. And I'm going to go through and make sure that I entered my values correctly. I'm going to look down the columns of the matrix in my calculator. 1, 4, 3, negative 5, negative 4, 7, 0, negative 1, 2, negative 3, 8, 6, negative 2, 5, 0, 9. So again, make sure that you have your determinant entered correctly. Now let's go to the home screen on our calculator. So I'm going to hit second mode. That gets me to the quit button. That's blue here. So second, quit. Back at the home screen, we're going to go back into the matrix menu. So second, matrix. We're going to choose the math option. And the very first option is det, which stands for determinant. So we'll take the determinant and now be specific about the matrix A we're looking at. So get second matrix and choose matrix A, option 1. So here then the determinant of our matrix ends up being 2042. Now it's a huge number, and in some examples that means something to us. In our class, we're just using this to be able to make the conclusion that A inverse exists, because this is not 0. Or to say it another way, we can say A is non-singular. Okay, let's move on. We've practiced taking the determinant. Now let's look at another application of the determinant, Cramer's rule. So we are wanting to know Cramer's rule is a method for solving systems of equations that have a unique solution one variable at a time. It finds the answer one variable at a time. To use Cramer's rule, the coefficient matrix A from your system of equations must be n by n. So you can only do this if your coefficient matrix A is a square matrix. And we require that the determinant of A be non-zero. This is ensuring that our matrix is non-singular and we have a solution. This will tell us that A inverse exists, or A is non-singular. Algebraically, you can see here that the determinant of A ends up being in the denominator of a fraction. And so if our determinant were 0, we'd be dividing by 0. So it's another way for us to verify that, yes, this determinant can't be 0. Now, how you do Cramer's rule? Your first step is let AI be the matrix obtained by replacing the ith column of A with B. So AI is going to be the matrix that's in the numerator of your fraction. And the determinant of A, your original matrix, is in the denominator. And so then Cramer's rule says the ith component of the solution is given by this fraction. I'd like to do an example right away so you can get a visualization of what this means to replace the ith column of A with B, because this has always been a little bit mysterious for some students what this means, how it's written. So let's look at an example. To apply Cramer's rule to this system of equations, I first want to write the matrix equation. So here, our matrix equation. Let's first grab our coefficient matrix. 1, 2, 2, 3 times our vector of variables, which will have the x, y, times our right-hand side, 5, 8. Now, Cramer's rule tells us that to find our solutions one variable at a time, so our first variable x is going to be equal to the determinant of AI, this matrix that's obtained by replacing the ith column or the x column with b, would look like, well, if you replace the x column, then the second column stays the same. But the vector b goes in the first column. And then you divide by the original matrix, or the determinant of the original matrix. For the y variable, again, you're dividing by the original matrix, or the determinant of the original matrix. Since we're looking for the y variable, which is your second column, we're going to replace the second column with your b vector. Okay. Notice that we've now written each variable written the solution to each variable individually, and they're each going to be a division of two determinants. And because these are 2 by 2 determinants, they're generally easy to take the determinant of. So let's do this first one. 5 times 3 is going to be 15. Minus 8 times 2 is 16. Divided by the determinant of the original matrix, which is going to be 1 times 3 is 3 minus 4. Which I think if I do this right, it's going to be -1 over -1, or just 1. The x value of our solution is 1. For our y variable, okay, we'll look at the product of the main diagonal, which is going to be 8, minus the product of our off diagonal, which is 10, divided by the determinant of our original matrix, which we already have from our x variable, which is -1. So y is going to be -2 over -1, or just +2. This tells us that our solution has to be the ordered pair 1, 2. Now, since this is the first time we've used Cramer's rule, I think it'd be worthy to verify that this is a solution. Let's imagine plugging in 1 and 2 for x and y. You will get back 5. Plug in 1 and 2 for the second equation. You do get back 8. So this is a solution to the system of equations. Okay, let's try this on one more example. This will be the last example we do today. Let's solve the following system of equations using Cramer's rule. And let's start again by first writing our matrix equation. Which means we first need our coefficient matrix. times our vector of variables. And this will have to equal our right-hand side. Now we'll apply Cramer's rule to find our solutions one variable at a time. So here then, our variable x now remember, for all of these, actually, they're going to have the same form to them, meaning the denominator is always going to have the determinant of your original coefficient matrix. So I'm going to try and be a little bit smooth with how I write this. Oh, I thought I could copy and paste this. Let me try that again. Copy, paste. Ah, it's not copy and pasting. Okay, I might just have to write it out. Okay, so let's continue then. Our y variable would still have the determinant of our original matrix underneath. And our z variable. Now for each of these, we're going to replace a different column of our original matrix with the b vector. When looking for the x variable, we're going to replace the first column. So it'll be 4, 3, 4. And then the rest of the columns look the same. When you get to your y variable, the first and the third column stay the same, but we replace the middle column with the b vector. And when we get to the z variable, the third column is what gets replaced by the b vector. Now, I'd like to pause here for a moment and give you a chance to calculate the determinants that are required here. And what you should notice is technically there are 4 different determinants that are required. And I think that is just crazy. To think about finding 4 different determinants to find the solution to this problem, when we have already seen other methods for calculating solutions of 3x3 systems of equations using our calculators. And so I don't want to continue doing this example because I actually am feeling that here Cramer's rule is a colossal waste of time. And I just wouldn't use Cramer's rule. I would apply a different technique that would be more efficient. However, if you are going to finish doing this example, what you should be able to verify here is that the determinant of your bottom original matrix would be -26. So all of these would have a negative 26 in the denominator. Your determinant of your upper matrix here for x would also be negative 26. That's just coincidence. For y, the determinant of your upper matrix would end up being 0. For z, the determinant of this upper matrix, again, ends up being negative 26. That's just coincidence. So that we can write our solution to our system of equations as negative 1, 0, negative 1. Now, although Cramer's rule feels like a colossal waste of time in this example, it does have great applications in future problems that we're going to look at, and so it's something I wanted to present. But I think this does give you everything you need to know for your homework for Chapter 3.4. So I'm going to end this video here. I hope this is helpful, and I'll see you next time.